Hello everyone, in this video we're going to pick up where we left off in section 11.3 with subsection 3, which is projections and vector components. So let u and v be non-zero vectors. Moreover, let u equal to w1 plus w2, where w1 is parallel to v and w2 is orthogonal to v as shown below. All right, so I've got this vector u, right, this guy right here, and then W1 and W2 are called the components of U. All right, so these guys are the components of U. And what do we have here? We have W1 is going to be parallel to V, right? V is this other vector that's inside of there as well, right? V is this guy right here. So W1 is going to be the one that is parallel to V, and then W2 is going to be the one that is perpendicular to V, right? And again, W1 and W2 are called the components of V. All right, so that's kind of what we're looking at here. And so W1, the one that is parallel, is going to be it's going to be called the projection of U onto V, or the vector component of U along V, and is denoted by this projection notation, projection of U onto V. The little subscript there means onto V. So W1, which is the projection of U onto V, is that guy. So I'm going to go ahead and kind of draw a picture here again of which vector that is. And then W2 is equal to U minus W1, if we think about how vector subtraction works. And that is called the vector component of U orthogonal to V. Why orthogonal to V? Because it makes a right angle with V, right? It is orthogonal. Okay, and let's go ahead and put this. This is what U is. And then there's also another picture when the angle is obtuse there, but the idea is still the same. Okay, so let's find the vector component of U that is orthogonal to V, given that W1, which is the projection of U onto V, is 8, 6, and U is equal to 5, 10, which is W1 plus W2. So everything is set up here in this example to match up with our definitions of projections and vector components, right? So because we have that U is equal to W1 plus W2, and W1, which equals to the projection of U onto V, is parallel to V. How do I know it's parallel to V? By definition, right? It's called the projection. And remember, what is the projection? That's that green one. That's the one that is on top of V, points in the same direction as V, right? So because U equals W1 plus W2, and W1 is parallel to V, it follows that W2 is the guy we're looking for, right? W2 is the vector component of U orthogonal to V, right? And so that is what we're trying to find. We are trying to find W sub 2. Well, W sub 2 is equal to, by our formula, U minus W1. Probably should have colored that in according to our guide. So what is U? We know U, that is 5, 10. And then what is W1? That's given by the problem, as 8, 6. And now we know how to subtract vectors. We just subtract component-wise. So here I get negative 3, 4. So that is my vector that is the vector component of U that is orthogonal to V. Okay, so let's look at this picture here to kind of talk about what's going on to draw our all of our pieces. So u is the vector we're kind of focused on. We've got our v is this guy right in here, right? Same as our v right in here. So we had been given by the problem the red guy, no, sorry, not the red guy, the green guy, right? We've been given the projection. We knew that that was 8, 6, that vector w sub 1. And what did we find? We found the orthogonal component, right, which was w2, right? And as you can see by looking at this here, if I were to maybe draw it in pink, I can see that this is a right angle, right? It looks like a right angle. And I could do the dot product between those two lines and see that it would be 0, right, if I really wanted to. But it is. And so we see here that w sub 2, the guy that we just found, which is equal to negative 3, 4, is orthogonal to RV, right, which is what we wanted, because it is the vector component of v orthogonal to v. Sorry, vector component of u orthogonal to v. Okay, so now let's look at projection using the dot product. So another way we can find the projection of u onto v is, right, actually in the other case we didn't find it, we were given it and we found something else. But now if I wanted to find it, here's my formula. So if u and v are non-zero vectors, then the projection of u onto v is given by this formula here. So it looks like u dot v over the magnitude of v squared times v, right? And that makes sense because this is just some scalar multiple, right? Because this guy right here, oops, this guy right here is a scalar, right? So it's some scalar multiple of v. And if we look at our picture back of what it means to be a projection, look, here's v, and then we just made this vector that goes in the same direction but a little bit longer. That's exactly what it means to be a scalar multiple, right? Okay, so the projection of u onto v can be written with a scalar multiple of a unit vector in the direction of v. Remember, unit vector in the direction of v, remember that was the magnitude of, sorry, it was v over the magnitude of v. Right? So I can rewrite this. I can say, okay, the projection of u onto v, which is given by the formula u dot v over top of v, the magnitude of v squared times v. Well, notice that the magnitude of v squared is just the magnitude of v times the magnitude of v. So I can rewrite this as u dot v over one of those magnitudes, and let's bring the other one out and multiply it times, so I would write it like multiply it times v, so this looks like this guy, right? And so now this piece right here is a scalar, we'll call it k, and this piece right here is, let's do a different color, let's do green, is the unit vector in the direction of v, right? This one right here is the unit vector in the direction of v, right? We learned that formula long ago. And then that k is just, I'm sorry, that u dot v over magnitude of v, we can just call it some scalar k times that unit vector, which is v over the magnitude of v. Right? And so that scalar that I just highlighted in orange, if I call it k, is u dot v over v, and that can also be thought of as u, the magnitude of u times cosine of theta, and that's because of the formula all the way back right here in orange. Right, so if I plug that formula in, then I would end up getting that that scalar k can be written as the magnitude of u times cosine of theta. And so that is called the component of u in the direction of v. That scalar is that magnitude of u times cosine of theta. So I guess I could highlight that in orange as well, right? Because that is what we're looking at. Okay, so the first question, example 4 here, let's find the projection of u onto v and the vector component of u orthogonal to v for these two vectors. Okay, so how do I find the projection of u onto v? That's the formula in the that I've kind of written in red. Right, so projection of u onto v is going, and order matters, right? Because it'd have something else if I did v onto u. So this is going to be u dot v over the magnitude of v squared times v. So I need to find all of these pieces. So u dot v, that's going to be the first component times first component, so 21 plus second component, so that's -5, so -5. Oops. And then third component times third component, so -4. So I get +12. And then the magnitude of v squared, remember we had that formula earlier that the magnitude squared is just it's just going to be the dot product of v with v. So this is going to be 7 squared, right? First component times first component plus second component times second component, so 1 squared plus -2 squared. So that is going to give me 54, right? So now plugging these values in, I get 12 over 54 times v, which was 7i plus j minus 2k. And then now multiplying my scalar throughout, I get 14 over 9i plus 2 over 9j minus 4 over 9k. So that is my projection of u onto v. So now the question says, find the vector component of u orthogonal to v for these two vectors. Unfortunately, if I had some sort of, if I had the angle between these two guys, I could use this formula right here, but I don't have that. So I just have to go back to when we introduced this. The vector component of u orthogonal to v is this vector w2, right? Remember that was the orthogonal one, and how do we do that? We just get u minus the projection, right? U minus w1, which is the projection. Right, so if this was the projection, which is w sub 1, then if the vector component of u orthogonal, to v is that vector w2, which is u minus w1, which was the projection, right? So w2 equals u minus w1 of the projection. So what is u? U is, we'll do this in the ijk notation, so 3i minus 5j plus 2k minus our orthogonal vector that we just, our projection vector that we just found, 14 over 9i plus 2 over 9j minus 4 over 9k. And if we subtract our component wise here, we end up getting 13 over 9i minus, sorry about the sirens, 47 over 9j plus 22 over 9k. And that is going to be my vector component of u orthogonal to v. So one cool application of, or another cool application of vectors in the dot product is work. So the work done by a constant force, so again, this is a constant force, not our integral force done by, that doesn't have, a constant force, but when work is done by a constant force F, acting along a line of motion, the object of an object is given by, remember, work is equal to the magnitude of the force times the distance, right? So force is a vector, just the magnitude of that vector times the distance, and it's a directed distance, so it's the vector PQ. And that instance is given by this picture here. All right, so if I have, this is my object, this box, and I am moving this box from point P over to point Q, then this is my directed distance from P to Q. All right, so maybe we'll draw that in the picture. This right here is my directed distance from P to Q, right? And so how do I find the magnitude of the force? Well, I take the magnitude of F times the magnitude of the directed line segment PQ. So now in terms of our projection, when the constant force F, that's supposed to say force, the constant force F is not directed along a line of motion, then the work done is given by the magnitude of projection of the force onto PQ times PQ. The magnitude of PQ. So remember, so this is when my force is acting directly in that direction. So in this case where my force maybe is directed somehow upward, right, if I'm not pushing exactly parallel to the direction I'm going, then I'll have to use this idea of projections and the orthogonal component and the parallel component, right? So that's where the projection comes in. And so if I direct my force at this angle theta, again, this is my directed line segment from P to Q. Right, this is PQ here. Then that's my formula. I do the magnitude of projection of the force vector onto PQ times the magnitude of PQ, which we can do some manipulation and find with some of our formulas from above and find that equals to cosine of the angle, right? Again, this is the angle right here. It's the angle that the force is acting with, times the magnitude of the force times the magnitude of the vector PQ. Okay, so that's essentially what our formula is for the definition of work. The work done by a constant force as its point of application moves along the vector PQ is one of the following. So it's either, you can think about it, this first one is going to be the projection form. And then, so I think about it obviously because it has projections in it, that's why it's called the projection form, right? And then going through the equal sign here, that's also equal to the force dot the directed line segment PQ, which is a vector, right? So this is the dot product. Okay, so in either case, notice that the work is a constant, right? Which is what we're expecting. Work is a constant. Force is a vector, but work is, we just get a number for it, right? And in both these cases, it's either a magnitude times a magnitude, which is a scalar, or a dot product, which is a scalar. Okay, so to close the sliding door, a person pulls on a rope with a constant force of 50 pounds at a constant angle of 60. Find the work done in moving the door 12 feet to its closed position, right? Okay, so here we're just going to use our projection form, right? Because the projection form is going to be really nice because if I look up here, let's do it lighter. When I write it as a projection form, then I can write it as cosine of the angle, which we're given the angle, times the magnitude of the force, which is what we're given, times the magnitude of PQ, or the line that it's moving, which again is basically just the distance that it's moving, which in this case the distance is going to be that 12 feet. Right, so what we're going to do here is using projection. Let's talk about all that we have first. So our theta, obviously given by the problem, that's right. So the idea is that you're pushing on this door, or you're pulling with a string to close this door, right? So the theta that you're pulling at, the angle is going to be that 60 degrees. The magnitude of the force, well, that is the 50 pounds. And then the magnitude of PQ is just the magnitude, or the length, right? Because remember, magnitude, we can also think about the length of the vector. So that's just the length of how far I'm going to do this pulling, and that distance is going to be the 12 feet, right? Or this guy, it's just kind of moved over because he's moved over 60 degrees, right? So magnitude of PQ is going to be that 12 feet. And now it's just a matter of plugging it into our formula that I have up here in blue, right? So work is equal to, given by that formula, it's the projection of F onto PQ times the magnitude of PQ, but we can rewrite this as cosine of theta, which in this case is going to be, we'll keep it as cosine of theta. Cosine of theta times the magnitude of the force times PQ, or the magnitude of PQ. And now plugging in all of our values, cosine of 60 degrees times the magnitude of the force, which we said was 50 pounds, times the magnitude of PQ, or the length of PQ, which is 12 feet, and that gives us 300 foot-pounds, right? Because remember, that's our unit for work. So that's our final answer there. All right, that's all I have for this video. Thank you.